Welcome to the MIT STM Systems Thinking webinar series. My name is Lois Slavin. I'm the Communications Director for STM. Welcome folks from around the world across industries who are here to listen to a presentation on how to analyze and visualize a large interconnected software system, a study of Fedora 20 with lessons for all. Before I introduce the presenters, I would like to ask the following, that you please mute yourself, that if you have any questions, you type them directly into the chat section addressed to everyone, and that there will be time for Q&A at the end of the presentation. Also, many of you have asked whether the presentation slides and the recording will be available. The answer is yes, they will by the end of this week, and a link will be sent to all registrants. With that, I'm going to turn this over to our presenters, Dr. Dan Sturtevant and Dave Allan.
Thanks, Lois. Thank you. Great. So today we're going to be talking about how to analyze and visualize a large interconnected software system. We use Fedora 20 as our example because it has a lot of interesting properties. You can think of it as a very large enterprise architecture. There are over 2,500 different software packages contained in Fedora. That compiles down to about 4,000 binary packages that get installed. We create a fully functional computer. It's a worldwide distributed community, but there are a lot of parallels between how you might think about that community and how you might think about a large enterprise architecture within a software firm. If you're an executive at a software firm, you might have thousands of teams with thousands of products, all of which interrelate with each other. There's complexity internal to those products, but there's also complexity in both the architecture of those products and also the architecture of how they're strung together. And that has significant organizational impacts. So that's what we're going to be talking about today. So engineering organizations and the technical systems they create are so complicated that no one understands them anymore. I'd say around the 1920s, 1930s, 1940s, humanity passed this threshold where the systems that we create are no longer understandable at all by a single human being. There are just too many disciplines. You'd have to go to school forever and get a bunch of degrees in order to really understand anything that we build today. You think about a Boeing airplane. There is no one in the world who understands why it flies, which is kind of scary to think about, but somehow it does. In software, these issues are magnified. Shapiro says that the fundamental nature of software involves basic and poorly understood problem-solving processes, multifaceted complexity. The word Cunningham, this is his quote, this is where the term technical debt came from. He said entire engineering organizations can be brought to a standstill under the debt load of an unconsolidated implementation. And as a result, software engineering over the past 50 years has been in a state of crisis. There was a study done by the Standish Group. This was looking at thousands of large software projects over the course of a decade, and they found that a little bit under 7% of those projects were successful. And what we mean by successful was that they came in on time, within budget, and the functionality they delivered was something approximating what they set out to deliver. 50% ended up landing, but failed for at least one of these dimensions, and the full 40% just were total failures. They were abandoned. They were started again from scratch. Those projects, the money sunk into them and the human effort sunk into them was just lost. And you can see this with plenty of examples out there. There's a Denver baggage control system that's a good case, but there are plenty of other systems, FAA and other large modernization efforts that you hear about all the time. And there's got to be something to this. I mean, you don't just have failure rates over 90% and feel like that should be normal. So what we're going to be talking about today, complexity within large technical systems, specifically software systems, the role that architecture plays in mediating that complexity and allowing us to cope even when there is no one person who can understand why that Boeing airplane flies, there are architectural properties you can build into it so that even though that's the case, everyone can, to some extent, understand their part and how they interact with their neighbors. And we're going to talk about the concept of technical debt, the idea that there might be shortcuts in a code base or some kind of technical system or other deficiencies that you built up over time that are causing you problems, right? They're causing you to be less productive than you otherwise would be, or to have more quality problems than you otherwise would have. It's analogous to going into financial debt. You can carry a little bit of it, but if you carry too much, you can go technically bankrupt, and then your project or organization might fail. We're going to talk about risk and operational performance and financial performance in large development enterprises. And then we're going to try to build some insight and improve outcomes using analysis and visualization. We're going to talk about that, and then we're going to look at the Fedora Linux project as an example, a motivating example, but it'll have lessons for anyone in a large organization or who might be in a small organization but has to interact with an ecosystem of other software products. Why do we fail? Modern systems exceed the bounds of human understandability. Right? I love this British Royal Academy of Engineering quote. It says that on a large software project, one is lucky if one person in 50 has anything resembling an overall understanding of the conceptual structure of a project, and divinely blessed if that person has the ability to explain it to anyone else. And this is, this again, it's the normal state of affairs, which is kind of scary. But my experience in the software engineering industry over a number of years says that this is true. It smacks me as reasonable, which is kind of scary. And this comes about because people are confused, right? You are embedded within a large thing. You don't have great visibility into it. You don't know why the components work the way they do. And ultimately that leads to risk, project non-delivery, safety concerns, operational problems, staff turnover. In really complex systems, you can talk to development managers and they say that people are trying to beat a path out of there. Delays, and you also have financial impact to the firm or the organization. So lost revenue, loss of customers, etc. And ultimately, this comes down to how well you can compete. If you're competing in a marketplace and you have these troubles and the competitor has, well, they probably still have those, but they might have fewer of them, then you're going to lose. So that begs the question: why do these architectures, or why do these systems work at all? Why do they ever work? Why does the Boeing airplane fly? Why does the internet function and whatnot? And the reason is the way we architect them. There are certain things that you can do. There are certain patterns that you can build into large-scale complex system to make it so that even though no one can understand the system in its totality, you can draw walls around things so that different people and different teams can understand their part and then understand the interfaces to their neighbors. And if you do that in an appropriate fashion, you stand a chance of being in a situation where the collective action among the developers of different parts of your technical system will result in something that actually functions. Now, that doesn't necessarily mean it's the most effective or efficient way of doing it, but you can only do so well when no one in the company actually knows why the thing works at all, which is, again, scary to think about. But you can build these patterns, and these are patterns that are, we see in nature too. If you look at any kind of complex organism, right, you see modularity. They're cellular organisms. You have cells. You have organs. These are parts that can evolve independently of each other without harming each other. So this also aids evolutionary processes. So getting more into why these things matter, right? Modularity is important because it prevents changes in one area from impacting others. For instance, it bounds communication requirements. Commonality is important. Layering is a very sort of strong form of modularity in some senses. It's a way of partitioning a system so that you don't have to think about anything on the other side of a barrier. Hierarchies are useful. So if you construct your complex system as a hierarchy of modules, that's sort of one thing people think of as an ideal way to go, because they prevent, imagine an org chart where there were cycles in it, where you were someone's boss, they were someone else's boss, and that person was your boss. It would make things very confusing. And ultimately, we also have to think about the quality of the individual parts as well. But we can reason about all of these properties, these architectural properties, as networks. We can think of them as directed links or edges between nodes, and we can think about modularity in terms of cohesion and coupling. So regions of a network where you have a lot of interconnections and interactions, and other regions where they're very loose. Commonality, you can think of these arrows going into something and it being reused a lot. So a lot of people thinking about system architecture or software architecture are reasoning about the high-level structure of these things as networks. This is just an aside, but let's get some notation out of the way. If we're thinking about networks, there are a few different ways to do it. These are two of them. Traditionally, when you think about a network of anything, you might see the pictures on the left. And on the left, you see nodes denoted by, say, the letters A, B, C, and D. You can think of those as source code files, right? So let's say D is a source code file which has a function call to a function that's defined in C, and C has a function call to a function defined in A. We would draw these arrows that way to say that D depends on C and C depends on A. And if you look down in the lower left, we'll see that we've added these two arrows that are indirect links. And the idea there is that D depends on A through C. What that means is that if someone breaks A, it could negatively impact D because it depends on it through C. That's what indirect links are, and those are very important. The fragility of your system is not just a function of the direct dependencies across different components. It's also a function of the indirect dependencies, the hidden dependencies that tie your system together in ways that might not be perceptible. Now, over on the right, we have a matrix view of a network. Some people call this a design structure matrix. It's an alternative way of viewing a network. It's good for some things. It's bad for others, but it's for some purposes it's very good at looking at architectural properties, and we'll get to that later. But the way to read this is that every dot in that matrix represents a link instead of a node now. So if you look at the dot at position the row C up to the column A, what that means is that C depends on A. Right? And if you look at the dot from row C to column B, that means that C depends on B. Also, you see that D depends on C. So we've got these three links in the upper right-hand matrix. Now that matrix corresponds exactly to the network that we see on the upper left. Likewise, if you look to the lower right, we've added these two links from D to A and D to B, and that is us adding the indirect dependencies in the design structure matrix. So we've got two analogous ways of looking at networks, and we're representing exactly the same thing. We're just looking at it in a slightly different way. So this is a picture out of Carlos Baldwin's book. She used motivating example here of motherboards. And so I guess the question is, what are these DSMs good for? What they're good for is helping us look at the relationship between technical components and also the teams that develop them. So if you look over at the picture on the left, we see a motherboard where different components are interlinked in all sorts of fascinating ways. Unfortunately, what this means is that Team A and Team B are highly coupled, right? They cannot operate independent of each other because something that Team A does may impact Team B, and something that Team B does might impact Team A. So they've got a circular dependency between them, which means that they need a high degree of coordination between those teams. And you look across the motherboard, and that's true for all of those teams. No one can act independently and just kind of race towards the finish line. In some ways, you could think of this as a three-legged race, except that you've got a lot of people and a lot of teams and all sorts of random limbs tied together. If you look at the right-hand picture, you see another motherboard, but people have used design rules to decouple these 4 modules so that the teams can operate independent of each other. Team A and Team B can now, innovate at their own clock speed. They can sort of race towards their own finish, and they can succeed independent of the other component, which means that innovation can proceed independently. The rate of return on research and development dollars can be substantially higher if my success doesn't depend also on you being able to accept my change into your technology. So that's the difference between an integral system and a modular system. Now, we at Silverthread have been looking at a lot of commercial code bases, and here's an example of one where modularity has broken down. So this is a DSM of a software system, and if you look at it, you'll see there's a strong vertical band up the middle. What that is a utility, right? So the idea that, remember, the way we read this is that if you read in from the columns and then read in from the rows and then read up the column, you're saying that lots of nodes in this DSM depend on that one, which means that lots of things depend on it. That means that the node or the file at that position is reused a lot. If you're a C programmer, that might be printf. The module that you see over on the lower right, would be fine as a module. And the way to think about modules is that if you have tightly interconnected files all clustered together in this DSM, they tend to form a square along the diagonal, and that's fine. I mean, if you constrain your complexity, your circular dependencies within a box, and have a single team working on it, then you have a module, right? The system is complex, but it's small enough that it's within the bounds of the human understanding, and one team can cope with it. Unfortunately, that square box was around 2,600 files, and I think 80 people were working on it, which means that there was no way that you could effectively operate in that piece of code without an IQ of 11,000. And as a result, all sorts of changes propagated and all sorts of unanticipated defects cropped in. So this is an example of one system that we at Silverthread have been looking at. Here's some other work that we've done with commercial firms. So if you look at the left-hand panel, this is looking within the context of a commercial firm. It happened to be a company with $1.7 billion in revenue. Looking at their code base, and we studied the technical architecture of the code, how it was constructed and how that mapped teams and human understanding, and found that developers, when they were working in the portion of the code base that was hierarchical and modular and had these nice boundaries sort of mediating the spaces between different parts and making it so that people could have a coherent mental model of a single piece without having to understand the whole rest of the thing. People that were in the good part of that system were able to produce 20,000 lines of code per year after you controlled out a bunch of other things. But people who were working in the part where those properties had broken down were only producing 8,000 lines of code per year, right? So if we did the math and went through some technical debt calculations and some estimates around refactoring and concluded that over $4 million within that particular organization was being wasted every year on sustaining technical debt, basically paying the interest on the technical debt of that system. Now in the middle panel, we've got a different commercial firm that we've worked with. This is a commercial firm that develops a lot of safety critical products. We looked at changes that had to be made to code bases after a product was released. And this was a safety critical system, so it was an embedded system. It wasn't a train, but I can't tell you what it was. But what we found is that after the software was released in the system and it was live, they had to fix a number of bugs. And when a system is live, you don't fix things willy-nilly, right? You don't change something because the color is off, right? You change it because it might crash. And what we found is that in the parts of the system where there was clean architecture that we could detect using our measurement algorithms, there were, it cost 12 cents per line of code to patch and maintain that part of the code base. And in the part where those properties have broken down, it was costing the organization 81 cents per line of code. This also obviously has safety implications. If they're changing that much code after the fact, then you wonder about the quality of the system. On the panel on the right, this is a third commercial firm that we have worked with. And again, we're scanning their code bases and measuring architectural properties and where they've broken down, and found that when you look between products with different levels of complexity, the organization with a less complex code base was 10% higher developer productivity during maintenance activities, 14% less time to release security patches, 25% fewer incomplete or incorrect fixes. Basically, this was an organization that maintained a lot of code. Here's a financial analysis of a refactoring effort, right? So we went through the estimates of the cost that complexity had for the organization, and basically estimated that if they refactored their code base in some reasonable way such that they drove complexity down, we were able to estimate that by freeing up developer activity, they would no longer have to fix as many bugs, and they would be more productive when developing features. So we can estimate based on reasonable estimates of complexity reduction how much more agile an organization is going to be. Now this is a final example of a commercial firm that we've worked with. This is a refactoring project, so there's a before and an after of refactoring, and I find this one fascinating. The company was very successful at doing their refactoring, and what they did was they had an engine, and they had programs that ran on top of that engine that could be customized for different purposes. And the problem with the pre-refactoring system was that the programs that were running on top of the platform were coupled cyclically to the platform itself, such that the development teams maintaining the user-facing programs could not operate independent of the people developing the platform. And as a result, they were all moving slower, and they all had more defects. Once that refactoring was complete, you see the trajectory dramatically shifts. This organization is capable of producing products at a much greater rate, and this has direct impact on their ability to generate revenue and go into new markets. So we're able to, again, look at complexity of an architecture, how that spans team boundaries, and the impact that has for revenue generation and competitiveness. In this case study, we're going to be looking at Fedora. And I'd like to hand this off to Dave, who works at Silverthread, and came to us from Red Hat, so he knows all about this, and should take over.
Right. So, yes, so I've been obviously using Fedora for some time as an ex-Red Hatter. But that's not really why we chose Fedora. We chose Fedora because it's a good example of a large-scale code base, a large project, that has the kinds of metadata that are useful in figuring out what development teams, or in the case of Fedora, what development communities, because Fedora is a distribution that's composed of thousands of software packages, each of which is produced by its own community, that might or might not talk to the sort of core Fedora project people. But one thing that they do have to do is they have to talk to one another, and it's the open source world, so nobody's forced to talk to each other if they don't want to. But in the process of producing features, it's necessary. If you depend on somebody else's library or somebody else's build system, as you go through the development of new features, you find yourself having to communicate with those folks, and it's either because they changed something and you need to respond to it, or because you want to change something and something needs to change in their work in order to implement that feature. And of course, Fedora being a distribution, in order to have a package installation system that makes any sense and is actually usable by the people who are running the operating system, you have to have the metadata to enumerate those dependencies. In other words, if I want to install, say, Firefox, that's going to depend on a whole bunch of other packages, and the package manager will, if I say I want to install Firefox, the package manager will develop that tree and install all the dependencies that aren't yet installed. So what that enables us to do is to build a graph of how the communities interact, because it's one thing to say that there's a technical dependency, like Firefox will not run without system libraries. That's a technical dependency. That's very well understood stuff. Every distribution does this. What's less clear is the relationships among the communities that are building these software packages. And that's really what we want to talk about here. So this, on the left, is a DSM of the technical dependencies among the packages. This is the, if I install Firefox, then I must install also the system libraries. These relationships are very, very hierarchical. As you can see, there aren't any of those clumps that we saw in the earlier DSMs, and we have a nice graph. So, and the, as you might expect, the dependencies flow from user-facing application software down through system libraries, and then down to the kernel. Now, what's interesting is that the communities are not so hierarchical. And this was a surprise to me, even having worked within those communities for many years. And what we discovered when we actually looked at the relationships of all of the packages, for example, if I want to build and run the kernel, what are all the communities that are involved in shipping a kernel that a user can install? And it turns out to be quite a bit larger than I had thought. And also, there are a number of things in it that are kind of surprising to me. And sort of the most surprising one, and this is a little bit of an out there example, but it turns out that the GStreamer plugins are in that group of communities. And when I first saw this, I sort of wondered if perhaps the data was wrong, because that didn't make any sense at all to me. And so we actually went back and looked very carefully to see what the dependencies are. Now, the dependencies of the GStreamer plugins to the kernel are obvious, and that's what's tracked in the package manager. GStreamer depends on glibc. glibc depends on the kernel. If you want to install GStreamer plugins, you really better have a running kernel, or you're not going to get very far. That's well understood. What's not so obvious is the other path back from the kernel to GStreamer. And that's a long path. There are 11 hops in that path. And what that means is not that, oh my goodness, if I install the kernel, I'm going to have to install GStreamer too. Obviously, that's not the case. What this means is that the development that's done in GStreamer plugins in a very distant way could possibly impact the kernel in terms of the kinds of conversations that need to happen to get a kernel built and installed. Now, how is this? So this is, again, this is a bit of an out there example, but we are really talking about effects, sort of the effect of the butterfly at the edge of the universe, which in a single instance is not large. It's in fact tiny. But when the graph is large, the sum of these interactions can be very, very large, and that's when you get into things like technical architecture review boards at large companies, and very stringent process to control the development within the core of the organization, because you have to be absolutely certain that you're not creating roadblocks that will end up in circular dependencies and then get amplified. So let's walk back through here, and basically what you see is that Well, GStreamer might have a bug that would affect Qt mobility, and then that might affect KDE Workspace. And each one of these things is not very large, and they're very closely related. But then when you walk back through the tree in its entirety, you end up with 700 packages. And anything you can do as a manager to reduce the size of that cyclic group is really going to reduce the possibility that you end up with a technical review board that nobody can get anything through. And that's where you get into the discussions of technical bankruptcy that Dan mentioned a minute ago.
So this might seem like a contrived example, and it sort of is, but if you think about the fact that, every day you might be blocked waiting for someone else on something, but you don't know what they're being blocked on, and you don't know what that person is being blocked on. And these cycles really can amplify the issue in imperceptible ways that are hidden to the individual, are hidden to the organization, and until you trace them out, you can be much less effective than you might otherwise be, and not even know it. This is sort of a trivial example, as Dave said, but if you consider the fact that these organizations have millions of such dependencies, then all of these low probability events or seemingly trivial events that only cost you a nickel, they add up. And when you add the cycles, you end up in a situation where they kind of run around in circles.
And that's a lot of nickels.
And that's a whole lot of nickels amplifying each other. And so this is why you think about Amazon, right? Amazon is known to be extraordinarily modular, both organizationally and in their code base. And as a result, they were able to pivot from a company that ships you books to someone who's the largest cloud provider, because they were able to develop capabilities independent, decoupled from each other, and then exploit them in ways that they didn't anticipate beforehand. In your typical company where they don't have such concerns and aren't as strict or rigid about architectural boundaries, there's no way you could do that. These companies might develop internal cloud capabilities or internal server capabilities, but they would do it in such a way that they wouldn't be able to be decoupled from business cases and whatnot. And as a result, you can look at Amazon's growth in market share relative to plenty of the other .com companies that came along at similar times. And it all speaks to not having too many links like this and strictly managing them, both organizationally and technically. So imagine that you are a lead, you lead an organization with 2,500 development teams, and they're working on interrelated products. What's a good strategy for deciding where to focus, right? So you have limited focus. You don't even know what all of them are. What do you do, right? So maybe you want to determine which of those products are most important from a revenue and competitive perspective, and obviously place focus on those, and that's what you would do naturally. But if you look at an analysis like this, you can see what products they depend on, right? Both directly and indirectly, by focusing sort of on the enterprise architecture. How are the teams structured, and how do the tools developed by one team get consumed by others, so that if a slowdown in one area can propagate, you might have inefficiencies that you're unaware of. You can figure out which products need attention even if they didn't seem important at first, and you can use technical debt measures. Again, we're showing you design structure matrices and network graphs, but again, we're computing out of those graphs metrics associated with complexity, both architectural and within component, and using that to trace back where there might be issues in that network. And then ultimately, you may want to attempt to break some of these links or eliminate hidden structure that impacts those teams if you can do a financial analysis. And these are some of the things we at Silverthread are working on. Technical debt balance sheets, for instance. How do you rationally decide whether to refactor something or rewrite it or leave it alone based on financial considerations, as opposed to just sticking your thumb up in the air and testing the wind. How do you make rational financial decisions using this kind of information about complexity, architecture, and technical debt? And if you do these types of things appropriately, then you might be able to speed up teams that are on the critical path or are the most important by attacking areas outside of teams are that might not be obvious, right? We did network analysis and we got to GStreamer from the kernel through 11 hops, for instance. Now, here are a few graphs. In the one on the left, now we've taken these individual components, so these 2,500 different packages, and we're plotting them. We're saying that the red ones are all the ones that are inside that cyclic group, so they depend on each other circularly. We see that we've called out the kernel explicitly, but all the other red ones are packages that could impact the kernel. And in the right graph, or on the left graph, we've plotted architectural complexity internal to a package against the size of the package, and what you can see is sort of a curve. Packages can't get that big and still be too complex because they'll just sort of crumble under their own weight. They get so big that no one can understand them anymore, and they either get refactored or they die. So that's why you see sort of a downward facing slope on this graph. The Linux kernel is known to be extremely clean and extremely well architected relative to many other things that are out there, and you see that as one of the biggest package, the biggest package over in the bottom right of the left pane. If you look in the right pane, here we've actually sized the bubbles based on the internal file complexity. So we're looking at the complexity of the files within those packages on average, and we see that the kernel's complexity within files is much lower. So its size is big. It's pretty good in terms of complexity of the files or functions or methods that it contains. But you can look at the other red dots, and we can trace the links and say, are any of those too high, right? We know that McCabe's cyclomatic complexity, for instance, has a very strong relationship with defects, and so if the kernel depends on something that has a high propensity for defects, then managerially we could say, not only does this thing have a high propensity for defects, but a lot of other things we care about depend on it, so we should focus on that. There might be other packages that have just as many defects or just as much complexity, but you don't care as much because they are not positioned within the network of products in such a way that they can harm as many others. Here are a few others, right? So in the left-hand side, we're looking at the direct coupling to other packages. So how interconnected are you directly to other products within this product portfolio? That's another way of looking at complexity. And then over on the right, we're looking at the architectural complexity within the package, right? So if we look at the way the files within a specific package are structured, again, now we're not looking at the organizational structure. Now we're looking at the technical architecture within a product. And on this measure, Linux is doing very well. But we see others that are not. And again, we could use these to rank and find areas of greatest risk, not just because there's risk internal to the product, but because they present risk to others in the ecosystem because of where they're positioned. So if you have something of low complexity or high complexity or low quality that's positioned in a dangerous place, that's where you want to focus. And these are the types of things that we can figure out through using a variety of different architecture and complexity algorithms, and then sorting them appropriately and finding where is the biggest bang for the buck. So now imagine that you want to focus in on an individual software team. We already went through this process managerially. First, you were an executive and you wanted to figure out what you were going to do within this enterprise, this large enterprise, to figure out which products to focus on. We can scope this down to say, okay, now we're inside of that product that we want to focus on. Where within it are there problems? Right? How do I gain visibility very quickly into where the problem areas are? And again, the problem areas, it's not just the complexity or the risk or the defects within individual components. It also, you also have to take into account how much those components can negatively impact others based on where they are positionally. If you introduce a bug in some places, it won't take down the rest of the system, whereas others will be well positioned even if they're just minor flaws. Now we can look specifically at the Linux kernel, right? So this is a DSM not of the organization as we showed before. The organization as we could see, teams and the products they produce and the interrelationships between them. Now we're looking at files within the Linux kernel, and we can see, we also have a shared or utility region over on the left. We have a core, and Linux has a very small core. And cores aren't necessarily bad. Every package is going to have complexity in it. It's neither good nor bad, but it's costly, and you just have to weigh that against the benefits of having that complexity because it adds functionality. But Linux is sort of known for having low complexity. But if you're managing the development process, you're going to want to treat the files in there differently, right? The people who are working there might need to have more experience. You may want to allocate more testing resources or test coverage. You might want to have more process around the release cycle. You might want to freeze that code earlier. So you could, if you ran this type of network analysis, you could figure out where you need to be more careful, where you need to allocate resources, and where your areas of highest risk happen to be. I'd say in that core, that's probably, if you know the Linux kernel, it's probably where the memory manager are. The memory manager and the scheduler happen to be, and some other pieces of functionality. So we've gone all the way up from you're an executive at the top of a large enterprise architecture, drilled down, weighed risk in different areas of a system in a way that is financially rational, and then scope that down to go within individual packages. So this is what we are doing. So I guess I should back up. My name is Dan Sturtevant. I'm the CEO of Silverthread. I graduated from ESD in 2013, and since we've started this, and I graduated from SDM in 2008, the master's program. I had a fabulous time, Lois, in SDM. It was a wonderful experience. Thank you so much. And since then, we've started this company called Silverthread. So it's me, Dave, who spoke, Sunny An, and also Carlos Baldwin, who's a professor at Harvard Business School, Allan McCormack, also at Harvard Business School, and Michael Davies, who's a faculty member in ESD. And we are now commercializing the research that we've all been doing for a number of years in this area. I'd like to throw out a few plugs. First of all, we started a technicaldebt.net website that is a community and academically oriented site. It's got a lot of research on it. It's got a lot of methods, explanation, and we're hoping to grow it into something that's a good community resource. And also, our commercial site is silverthreadinc.com. And we would love to have the opportunity to scan and analyze your code. We'd be happy to look at a little bit of your code for free with you. If you reach out to us via our website, or via email, if you want to contact us directly using just my email address. So with that, I think I will end.
Great. Thank you both very much. If anyone has any questions for Dan and Dave, please type them directly into the chat section and address to everyone. I will then read them aloud. Here's the first one. You talked about Amazon through this lens. Can you talk about Microsoft versus Apple through this lens?
Where should we start? Apple's interesting because Apple's operating system now, one of the smartest things they ever did was switch to a BSD operating system. So they're underneath it's all Unix. One of the things I think either Apple was brilliant or lucky, but one of the things about open source is that it's great at developing system code and terrible at developing user-facing code, like GUIs that are. And it's, well, okay, I've been looking at it for 15 years. I haven't seen a GUI yet that's any good, right? But it may be that just GUIs, developing good GUIs requires code that's more integral, right? Open source communities are really good at developing highly modular, decoupled code, and I think something about GUIs might just require it to be more integral. I think open source communities, because they are distributed and the communication channels are weak and intermittent, it might be really hard to develop something that requires more integrality in a system, and so GUIs just might be in that bucket. So if that's the case, then Apple's brilliant, because they just let the open source community develop their kernel, and then they are responsible for look and feel, and they can do that in their cult, in their headquarters.
I also think that open source, one of the, I think, frequent causes of technical debt is commercial pressure, where it's totally rational for an organization to take on technical debt to meet a market need. And, of course, open source communities, because they're not selling anything, have a degree of immunity to that kind of pressure. And so I think, as a result, some of the tendency for open source projects to be well structured maybe is a result of that. In other words, they don't have any, other than the work required, there's no unwillingness to refactor something that's gross and to get rid of technical debt. So I think that's a benefit, especially in the, as Dan says, the low-level library kind of case.
Great. The next question is from Davi Eddy, who asks, what sorts of applications do you look at, and what kinds of languages do you examine?
Sure. Well, I mean, we've shown you graphs today out of Fedora, but for our customers, we actually have a whole lot of other data points that we include in those graphs, which are a bunch of commercial examples, which we can't really share, in an online forum. But we have analyzed C, C++, Ada, Java, C#, Python, COBOL. I think that's Fortran. And we could look at others as well, all through the sort of the same lens.
Okay. Next, we have a question from Aisha Alomer, which is, how big is Silverthread, and can you please explain how you have been able to scale it over the years? Do you believe that the highly educated partners have given you a competitive advantage over your competitors?
Well, we're actually pretty new, so I wouldn't say that we've scaled that big yet. Highly educated partners? What's that mean?
Professor Corliss, maybe?
Oh, our professor? Yeah, I mean, well, Allan and Carlos and Michael, I mean, they're actively involved. Allan and Carlos have, invented a lot of these methods and have been engaged in these research over the past 10 years, and that's obviously very, very, very helpful. And I had the pleasure of being able to work with Allan for 5 or 6, and now Carlos for the past few, and it's been great. So I think being able to work with people who are experts in something is an obvious benefit that we can't deny, certainly.
Okay. From Jason Slybeck, are there structures other than hierarchies that will work? For example, how would this analysis apply to a cellular organization?
Cellular meaning modular?
Do you mean modular, Jason?
I mean, in some ways, open source, in a lot of ways, they're just anarchist cells, right? And that's really about modularity. So, I mean, there are a lot of different architectural patterns you can reason about. Layering, commonality, hierarchy, modularity. You can reason about APIs, and a lot of these things you can get at by analyzing entities and links. But you might need some other information you pull in that's language specific. There are special things you have to do around static analysis versus runtime analysis. You have to worry about other types of things that you can't get via static analysis. You can do special instrumentation to get at some of those. But I'd say that in order to be well-rounded about architecture, you have to look at not just hierarchy or modularity. Or you have to look at them in different ways and in different combinations.
Great. Thank you. From Teresa Ray, the focus of your presentation presentation, at least in part, was modularizing code so that multiple groups could easily work on the code and so that issues in one module would not widely impact other modules. How do you ensure that these modules are integrated? Do you have teams assigned integration duties separate from the individual modules who view the solution from an overall system standpoint?
Well, so let's just take that. I'll assume that we're taking that from the perspective of Fedora, and then I'll just pass it over to Dave.
So, right. I mean, in some ways, I think this is a question that goes well beyond the scope of what we've presented here. I think, yes. I mean, historically, I think speaking specifically of test efforts, what I've seen and what I think is pretty common across the industry is that you have to have a mix of unit testing and integration testing. If you have one without the other, you really don't have a complete strategy. And especially with modern interpreted languages, having a full suite of testing is really key, and integration is a key part of that. I hope that answers the question.
Okay. Sorry for the delay. From Christopher Hoffman, on the DSM and network diagram slide, you showed indirect dependencies with the same notation as direct links. In actual application during analysis, how do you prevent the entire matrix being filled?
Do some network diagrams that you should. Well, there are a few different. In software applications that we're using to do this kind of stuff, we have algorithms that can treat it both as a network and treat the underlying data structures as networks and also as matrices. Right? We can pick and choose. So we can walk this using depth first searches or breadth first searches or other types of searches, or we could use matrix algorithms like matrix multiplication. There are matrix multiplication algorithms you can use to say, I want to see one hop out. I want to see A to B to C, and then add the link from A to C, but not go further than that. So you could do it, steps out using matrix algorithms. You can also use network algorithms to walk the graph in a variety of different ways if you want to see different things.
Okay, thank you. From Julian Johnson, is there any way you can analyze code which is not releasable to you due to IP or security constraints?
Yes, we have the ability to, we could send you a code that would collect metadata. So as long as you were comfortable with the metadata and we came up with an appropriate way of scrubbing it or cleaning it so that you were comfortable with what we saw, we could do that. Now that being said, that makes everything more difficult. So it makes everything harder. So we'd want to have some serious conversations about what that meant. But it's certainly not out of the question. We obviously prefer to be able to have access to the code.
Okay. From Daniel, do you have thoughts on modularizing organizations, not just code?
Well, and that's kind of what we were talking about in the Fedora case, right? There are these ideas that mirroring hypotheses and whatnot. All sorts of academics have talked about the relationship between the organizational structure and the technical artifact that it produces, and which came first, the chicken or the egg. Amazon has a whole, the Bezos Manifesto talks about these kinds of things, right? You should have 2 pizza teams, teams that are small enough that you can feed them with just 2 pizzas, and if you get beyond that, you got to break them up some more. So I think they have rules around their APIs, and they also have comparable rules about their teams. So that's one example. I don't know, Dave, do you have another?
Right. And I guess the thing that I was going to add is that you really want to, I think most successful software organizations have an understanding of the bits of the system that are sort of key to its functioning and need to be subjected to some sort of commit control process or enhanced vetting, and the bits that don't. The part, I guess, that was surprising to me looking at the Fedora system, even though it's a system in which I've worked for years, was the size of that group. I mean, I would, just off the top of my head, I mean, I wasn't a kernel guy, but I would have put the kernel in that group, I would have put libc in that group, and then after that I would have trailed off fairly quickly, sort of saying, well, everything else is not really core. But it turns out that when you actually look at the network relationships, that grouping is quite a bit larger than I would have suspected. So I think you have to be really hard-headed about what those relationships are and make sure that you put the appropriate level of review onto changes in those areas.
And you know, there are probably a lot of them that make sense, right? You can't just easily pull them out. But the example that we had with the 11 links from the kernel, where the kernel depended on it, you know, that's one where, you know, someone really should sit down and think about it. I think they probably already have.
Yeah.
Does
this really have to be a link?
I think
or can we break this?
That might be a mistake, right? So think hard about the ones that are obviously low-hanging fruit.
Okay. From Mike Johnson, are you using these techniques to analyze the social networks of the companies you work with? The thought being to understand software developed in different areas of the company where the social network is not in place and there is or could be duplication of effort.
The answer is yes. We've done a lot of thought about that, and we've done some work in those areas. You know, you can think about, you know, silly questions like, let's say you're going to buy a software firm, and you're doing due diligence. You know, one question is, which developers need the golden handcuffs, right? Which developers are working at the nexus between two components that no one else knows, you know, that interface well. And, you know, you can do some estimates and say that, wow, the learning curve in that part of the code base is 2 years long. So those are the kinds of things that you might ask if you're thinking about, we can mine information out of management systems, not just code bases, but version control systems, issue tracking systems, HR databases, project management systems, and then reason about, you know, where are people working. We can trace the logs to figure out, you know, which individuals are working in which parts of the code base and what are they doing, right? Are they fixing bugs? Are they implementing features? Are they committing code, you know, on Tuesday afternoon, or are they working, you know, late Sunday night, you know, because they might be more likely to introduce defects then, right? So there's all sorts of analysis you can do about the people to better understand what's going on with the company.
Okay, I'm going to jump ahead to Shyam's question, which is, has your software been used to confirm or disprove Conway's law?
I'm unwilling to put a stake in the ground with one data point.
Agreed.
Two makes a trend, sort of, but one certainly doesn't. So.
Okay, now we have two questions from Dheeraj. We will wrap up after those answers are given. That said, if you have questions, please do enter them into the chat section, and we will be including Dan's and Dave's contact info. Actually, you can even see it right there on the slide. So you can contact them directly to discuss it, and you're entering the question will give them a heads up that you'll be in touch. The next two questions are from Dheeraj, who asks, do you have any suggestions for beginners on getting started with DSM analysis, such as resources, best practices, pitfalls to avoid that would help one get started? Particularly, he or she is particularly interested in something that is amenable to self-education.
DSM analysis. As far as resources go, we have this technical debt that you could go to our websites, and we have links to a variety of papers around technical debt and these sorts of methods if you wanted to start there. There are links to obviously Allan and Carlos's papers, but a number of other people in the community. I think Allan and Carlos's papers are great. Carlos wrote a good book called Design Rules about 10 years ago, that kind of goes through the history, uses DSMs to analyze the evolution of the computer industry around the 60s. And that was a really good sort of look into the relationship between technical architecture and sort of ecosystem performance. Steve Eppinger, who is a professor here at MIT, has done a lot of work in that area, so you might want to talk to him. And he has a book on design structure matrix methods that's sort of a survey of a lot of different people's work. So if you want a survey on that, that's a good place to work. And then, a DSM is a matrix or a network, so you need a matrix or a network software package. MATLAB's a good one. If you are, looking for something that's, for non-computer scientists to learn, and there are plenty of packages for people who are trained in computer science.
Great. We are just at 1 minute past 1 o'clock. If we have one more question, if you wouldn't mind staying to answer that. But for those of you who have to sign off, I'd like to say thank you for attending. Again, you will be getting the contact information from both presenters, and you can contact them directly with any questions. And I would like to invite you to our next webinar, which is on February 9th, 2015. It's on formalizing the conceptual modeling thought process to benefit engineers and scientists, or to sum it up in one small sentence, to model or not to model. You will be given information on that in about 2 weeks. So thank you very, very much for attending, and I'm going to go back to the last question here from D-Raj, who says he's curious as to how you got started with this subject.
I was in the software industry for a long time, and I was a developer in a variety of different organizations. And sometimes when I worked in a company on a code base, I would want to implement some functionality and it would just work. And then I'd want to twist it to do something new and it would just work. And I would, abuse the thing and it would just work, with minimal effort. And then I would go to, and I'd work in other environments with equally smart people and code that looked equally clean, but every time you touched it, something else broke. And then you do something trivial, and then someone would call yelling from 3 buildings over, and your productivity was, half of what it was elsewhere, and it was extremely frustrating. I didn't really have a good way of thinking about that or explaining why that necessarily was, but when I was in grad school here at MIT, I was talking with Michael Davies, who teaches in ESD, and he said that I should really go speak with Allan McCormack, because he thought he might have some insight. So I read Allan's papers, and kind of a light bulb went on, and I said, that's what's happening, right? It's these indirect links that span the organizational boundaries that I cannot see, right? That's why, and it's in the technical architecture, so every time I make a change, it's breaking something that I have no idea what it even is, because it went through a bunch of indirect links. So I went back and I tested that in a variety of circumstances and found out that, yeah, that really had a lot of explanatory power for my own history as a software engineer. So that was my experience. And then I think Dave and I both have the same experience as far as what convinced us. And what's interesting about Allan and Carlos, what's fascinating about them, is that they came up with this method that I think is incredibly powerful. And neither of them, has a lot of experience writing much code at all, right? I mean, they're in a business school, and Allan's written some code, and they've both done a little bit of that. And they're obviously very smart and technically proficient people, but their methods, they ran an algorithm on the Linux kernel and found that in order to reduce complexity, the file that you could pull out of the network to reduce the complexity the most was the Linux tape driver. And a floppy tape, right? this is something you use for backups, and it's from, I don't know, God, the 80s or 90s or something, right? And so you pop this tape in, and it records your data, and then you pop it out. And this is probably one of the worst pieces of functionality I've seen in the kernel ever, right? So their method, with no knowledge of the internals of the kernel, they came to me and Allan said, it's the tape driver. Who knew? I don't even know what that does. And I personally had experience in the kernel. I said, yeah, that thing's horrible, right? Of course. And looking back on it, it's interesting because the Unix architecture has, a concept of a block device. I'm going to get geeky now, right? So it has a concept of a block device and a char device. And the people who designed device drivers in the Unix operating system, or the concept for them, didn't anticipate something that was a weird combination of the two. And so it's sort of, it's got wind blowing in from both sides that's affecting it, and so it's just terrible. And it's because it violates, the idea of such a thing violates the original intent of the architecture. And so it's just this festering thing that's just been sitting there forever. So the fact that Allan could identify this without even knowing what it was or why, and it, struck me, said that, okay, they're really onto something real here. That was my experience, and I think, I don't know.
Yeah, well, that particular piece of data I found very interesting. But I also, early on in my career, I had seen a lot of software products that had gone through several iterations, and they seemed to have a kind of repeating cycle where the first couple of versions would come out and everything would be very smooth and very functional, and then they would have this kind of decay curve where you'd go through a couple of releases of decreasing quality, and then the company would go out of business. And then, sort of very early in my career, I actually worked for a company that experienced some of these things, and it became clear that software complexity was really at the root of this, but I didn't have an analytical framework to apply to it. And so when Dan and I got together, just the opportunity to actually quantify this stuff and put some metrics behind the management was really appealing.
That's great. Thank you very much, Dave. And Dan, thank you all for attending, and have a wonderful week.